Can you see well the screen from there? The color is okay? If I open the Excel file, can you see the numbers? Yeah. Okay. If not, let me know. We will try to switch off the lights. Okay? So, welcome to day 4. We are going to finish. We left an exercise pending from yesterday. So we have to finish that. So we are now talking about dry gas, which is very important. It's even though it sounds like a simple case, you can use this equation for many cases. Okay. So we already were looking at the problem. If we have either PWF, how do I calculate PWF? Or if I have PWF, how do I calculate PWH? Okay, that problem is clear. We are all masters in solving that problem. Okay, but now what we said is, well, I want to know what will be the pressure along the tubing in some positions that I have. Okay, let's say that I have all of these positions. Okay, first I make a point. Okay, and then here, for example, I have, how many points will this be? 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so I make 8 points in the tubing where I want to calculate the pressure. Okay, and all other properties. So I call now the segment. Okay, what are the segments? This will be the segment 1, segment 2, 3, 4, 4. Okay, and you see that if I have 8 points in the tubing, and each one of them, they have their own TBD, right? If TBD, I measure it from here, or MD, then point 1, 8 will have 0, 7 will have a few meters down, and so forth. Okay, so what we said is, well, in this case, I cannot just apply the equation from top to bottom or bottom to top. Okay, I have to apply it to find this point, okay, P2. Here I will have P2, P3, and so forth. Okay, but if you see, in essence, it's the same problem. The only thing is that the pipe segment is shorter. Okay, the space in the tubing that we're looking at is now this piece of pipe. If we now try to open up, or if we now try to split, okay, we will have segment 1, which will be PWF, and here you'll have P2 out, okay, with a rate coming of gas. Now you look at the next segment, okay, here you will have the same P2, but at the outlet you will have P3, and this will be segment 2, and so forth. So you have a bunch of other segments until, in this case, I think in our exercise we have a bit more, but we have here P7, and at the end I have PWH. Okay. So my P, this is P8, okay? On this one, or? No. This one is, let's see, that's the first segment, okay? Let me put the number of the segment here. Segment 1, I enter with PWF, and I come out with P2. Yes? Now segment 2, which is this one, yeah, I have the number here. So that one comes in with P2 and comes out with P3. Yes? P2 and comes out with P3. This is a 3, I think. So, okay, so let me see, like that, okay? And so forth. So what I have done is divide and conquer, okay? What the Romans did a long time ago. I I have a big tubing, I have an equation how to solve that big tubing, but I'm going to have now cut and have a lot of small tubings, and I'm going to apply the same equation to each one of these small tubings. And I have to start from the boundary, where I know the pressure. Okay, in that case, I know the pressure in PWH, so I'm going to move down, okay? And to calculate P7, then with P7, I go to the next segment, I calculate P6, I calculate P5, and so forth. However, so each segment has something nice, that they have the same standard condition rate, right? All the segments will have the same rate. So that's something that simplifies my life. Something that doesn't simplify it so much is that each segment has its own CT7 and S7. This one will have CT2 and S2, CT1 and S1. Okay? Each one of them will have their own tubing constant, segment constant, and their own elevation coefficient. So that's part of the complexity. Okay, so what we have done last class was we had these are the points, right? In this case, we don't have, so yeah, here we should have put like a point, okay, point number. That is the temperature measured in each point, or assume, yeah, we assume a linear profile. Then we know to calculate this S, right? And this CT, we need the average temperature and the average deviation factor. So the temperature, we say we need the temperature of the segment. And also now don't be confused. This is the average. You see it doesn't go all the way down because this is not representing the point number 1, okay? But it's representing segment number 1. Okay, T average, this is the T average of the segment that exists between 0 and 284. And this 362 is the average temperature of the segment that exists between 284 and 597, and so forth. So that's why it's missing 1 here. Now, about pressure, to calculate the C average, I need a pressure. And I don't have any idea, that's what we want to calculate. But if you remember, when we have analyzed the whole tubing, right, we said, well, pressure we can assume because it doesn't affect very much this constant. So let's make as a first approximation, we assume, okay? And we assume a number of, we assume 5, I think, okay? But you could have assumed any other number, okay? You ask me, I say 5, you ask another one, I say 10, 20, so each person will give you a different number. The thing is that you can assume any number, any number. Well, you're going to verify the thing that is important. If you assume any number, you verify it later. That's the most important. Okay, you verify if that number that you assume was correct or not. Okay, let's say that you assume here that it will be 10 bar. Obrigado. So let's say we assume now 10. Okay, I have put here, I assume a difference of 10 bar. Okay, and here I get 140. What doesn't make really sense if you assume a number where the pressure that you obtain down here is reservoir pressure. Okay? Why? Because you know if you have flowing, you have flow. To have flow, you have to be operating at a lower pressure than reservoir pressure, right? Okay, because you have flow. So you cannot have, if you have the same pressure at bottom hole than reservoir pressure, you have no flow. So the pressure has to be lower. In that case, the pressure is lower, but I really have no idea if that value is correct or not. So we assume, calculate the P average of the segment in the same way we have done with temperature. and we calculate this average deviation factor. Okay. After that, we have all we need to calculate S only for that segment. Remember, we're calculating C and S only for that segment. Okay. And then we start from the point that we know the pressure, which is the wellhead. Okay. We have pressure at the wellhead. We find the inlet pressure at the pressure either at this position, or it's called the pressure at the inlet of that segment, of the first segment. Okay, the pressure at the inlet of the second segment. It doesn't work if you start the other way, because you don't have the pressure bottom hole. Okay, so you have to start from the top. I have P2, I calculate P1. Then I have my new P2. Now I have P2, I want to calculate P1 sequentially. And you see that the number is significantly different. Okay, you see that the number that you assume for each point now is 46. It should be, it should be 46 and it's 50. What I assume is 60 and it's 52. Is very different one from each other. Okay, so a way to correct that, I told you, I just copy this number that I assumed. Okay, and I just paste it here. I make like a better assumption. Okay, now you see the numbers are much closer. Okay, so I have corrected my assumption. I just had the assumption to find an initial pressure value, and then I recalculate the CT, and then now I find the real number. Usually 2 iterations is enough. 1 iteration is enough in that case. If you ask me, I would say really the difference between 73.3, 73.4 is essentially the same. Now, why are we doing all of that, right? Why do we want to calculate pressure? Well, one of the things I told you is this tubing size, okay? And the thing we want to know is the velocity. The velocity defines many things of the gas. Defines if I will be able to carry out the liquids, defines erosion, defines friction, defines many, many different things. So the first step, we say we want pressure, we want temperature, because these are 2 things that I need to calculate. The BG, and then after the BG, the density, and then I need the velocity. Okay, so that was the other step we did yesterday. We said, well, now I have P, and I have my real T. I calculate the set, but that's not of the segment. Check, I have exactly the same number of points. So that's not a segment, that's in that point. At that depth, I have that set. At that depth, I have that set. Now I have set, and I have P and T, so I have everything I need to calculate BG. But here we have to be careful. Remember that the pressure has to be in bar, that's fine. But the temperature had to be input in Celsius. And here we have been working in Kelvin. So I have to subtract 273.15. This one should be blocked, 0.55. And the unit 2 if you are using metric or metric system. BG, exactly the same. I need P in bar, T in Celsius. So it should be B15, that's correct. C, the deviation factor, I'm using this guy here, J15, and I'm using in metric. And just like a quality check, I check the number. Okay? The number seems to be okay. Okay, it's usually like that. It's in the range of 1 minus 2, 1 to the minus 3. And now I have the BG, and I have the standard condition rate, which is the same for all of them, and I use this conversion, which is very practical. Okay, I convert from standard to local conditions. Okay, and if you see, we get exactly the behavior we were discussing during the first day. That if the pressure is lower, the local rate is high. Okay, if the pressure is higher, the local rate is low. Okay, so I hope you have the same, you have reached the same point that I have reached. So let's try now to calculate the rest. Okay, we are going to do now in class only 2 checks, for erosion and for liquid loading. Okay, you can do also other things, But let's do these two checks first. So we need the velocity of the fluid in that, of the gas in that location. How do I calculate velocity?
The flow rate over area.
Divided by area, okay, the cross-section area of the pipe. So let's see if I have the area someplace. I think I have. The tubing size ID is here. And the cross-section area is here, which is just the pi times the diameter squared divided by 4. Okay, so that's the number. But be careful, we have to be careful. We want the velocity in meters per second. So I have to divide the rate divided by the cross-section area, and I have to do something else. What do I have to do?
Divided by 24 and 3,000.
Okay, because of the units, okay? Because if you remember, we are dividing Q. Okay, we are saying that Q of gas, remember, doesn't have the hat, so it's local, divided by the area is equal to the velocity of the gas. However, this guy is cubic meter per day, and this guy is in square meters, and I want the velocity to be in meters per second. Okay, therefore I have to include this conversion factor, that is 1 day are 24 hours and 1 hour is 3600 seconds. Okay, such that this day cancels out with this day, this hour with this hour, I end up with meters per second. Okay, exactly what I wanted. So let's do that to calculate local velocity. Rate divided by cross-section area, which is here, I block it, F4 times 24 times 100. And I'm getting a number of 52. Now, for those of you who took fluid mechanics, is that a high number or a low number? Very high, okay? When we talk about liquid, it's something around, should be maybe 2, 3, 1 meter per second, liquid. And gas, it can go up to maybe 30, okay, 35. But it's usually below that, between 15 and 30. So 50 is a very high number. That already gives you a trigger that you might have issues there, you might have problems. So if you want to keep producing that rate, what is the solution for that tubing? Just to make it bigger, right? Choke if, that's right, choke if you want to reduce the rate. But if I want to still make the same amount of money, I have to put a bigger tubing to avoid erosion. Okay? Or I have to change the tubing every. Okay, so if you remember what we discussed yesterday, we were saying that, so let's do the first checkup. Okay, the first checkup was erosion. Okay, and erosion, we were saying that the velocity of the gas should be less or equal than a constant called C divided by the square root of the density, okay, according to a standard called API 14E. And of course here where we're using field units, so we have to do some conversion, okay, because that's in field units. Yeah? D? Density of the mixture, okay? Remember that we are saying that not only, normally we're not producing just gas, but also sand, you might be producing liquids, so that's the density of the whole thing. Mixture, this will be gas, sand, is usually liquid also. Okay? because it has something to do with the kinetic energy. When it hits something, it depends on the mass. Okay, the mass depends on the density. So we're going to now, so we have this guy here, okay, and we want to calculate now this guy, okay, the erosion, critical erosional velocity. So for that, so if you say this criteria is like the velocity of the gas has to be less than the velocity critical of erosion. Okay, and that's what we're going to compute. Okay, we have that guy which is a constant. We are going to use, I think, 100. We will see now the equation. But I need the density. And we are going to assume, just to make our life simple, that we have nothing else but gas. Okay, we have no sand, we have no liquid, nothing. We have just gas. So we need the density of the gas. We are going to say the density of the mixture is essentially the density of the gas. Very close. Okay, so to calculate the density of the gas, how do I calculate it, if you remember? Of the gas. The density of the gas, if you, is pressure divided by R set T, right? Yes? Okay, so that equation is programmed for you when we have, and we have everything we need, right? We have P, we have T, we have Z, so we have everything we need. So let's look at the equation that we are going to use, alt F11. Let's go down. You should have here density, okay? And here I need the temperature in Celsius, the pressure in bar, the deviation factor, and the molecular and the specific gravity of the gas. So let's use that equation, okay? Density, so I call it here, function, user defined, and it was called D density. The pressure in bar, I don't have to make any change, right? Now the temperature has to be in, sorry, this one, then the temperature is B and has to be in Celsius, so I have to subtract 273.15 to take it to Celsius. Set the deviation factor, I already have it here calculated. And then let's see, is up here, right? Someplace here. And that one I have to block. And you see the number that I'm getting, 22. I told you when pressure is low, that density is a bit close to 1 or the air. But we will see what happens when we increase pressure. Okay, you will see what happens. 22, and now I drag it down, and then I have 47. Okay? So that's this guy at the bottom here, okay, in this equation. So if the erosional, okay, the maximum velocity I can get according to that equation is equal to C over the density of the gas. Okay, so if the density of the gas is increasing, okay, so what happens if the density of the gas is increasing? The critical velocity will decrease. Yes? That correct? The erosional will decrease. Let's see if that's correct. Okay, let's calculate it. So if you go to alt F11, that should be, I think it's here in auxiliaries. Okay, you see the erosional depends only on the density of the mixture. It's exactly that expression that I showed you here. Okay. So density of the mixture, I changed the units because the equation is supposed to be used in field units, and here I'm using a factor of 100, okay, which is conservative. I could have used 120. Okay, so that will give me in meters per second. So let's use that equation for the next column and see how it behaves. So I find my function B erosional, V okay, depends only on one parameter, very simple function, on the density. Okay, and it gave me 26, and here's 17. So was it correct? Density goes high, and then this one goes down. Okay, which makes sense. When you have a denser fluid, hits harder, and then the velocity to start taking material out of the walls, it can be lower. Okay, it's like if you have, what makes more damage? A train with passengers that knocks the wall, or a motorcycle that knocks the wall? Okay, the train, right? What makes more damage? If you go at the same speed, a train or a motorcycle against the wall? Huh? The train, right? Because of the mass. Okay, so that's exactly what we're looking here. So see, there is some variation, but not really very much. And you see, in every place, so what happens if my velocity is bigger than this erosional velocity? Okay, that's what is happening. Okay, the velocity of the gas is greater than the erosional velocity. I'm going to have erosion on the pipe, right? Yes? Okay, because I'm overpassing the limit by 14E, IPI 14E. So I suggest we make that plot, okay, just to see how it looks like. And let's plot it here. And here is going to be a bit tricky. We are going to put, yeah. So let's see how it's going to be. So let's right click, let's add the data. Let's add, so let's say gas V or VG, B gas. Okay. And on the X, that will be, on the X we want to put velocity. It will be this guy here, M. And on the Y, we are going to put TVD, okay, true vertical depth. Yes? Can you speak louder? I don't have very good hearing, so can you speak louder? Some different number? Yeah, which column are you talking? This one? This one? Okay. Yes? You found the error? Okay, this plot is very important, so I recommend you, even this is not an exercise to deliver, I recommend you to do it. Okay, because this is very powerful. It's a plot we use pretty much in production engineering. Okay, this plot. So I have plot here, they are in the same scale. Okay, that's velocity oops, and pressure. I'm not sure if we can put it on a secondary axis. Let's see. No. No. So let's just change, instead of pressure, that will be pressure, or can also be velocity. Okay, and that will be V and in meters per second. Okay, let's change, because now the scale will be also velocity, and I want also to show values lower than 30. Okay, and let me add also the legend, okay, to know exactly what we are plotting. Okay, so see, when pressure goes down, okay, that's the bottom of the tubing, and that's the top of the tubing. When pressure is going down, velocity is increasing dramatically, okay, which was what we already discussed. Okay, now I'm going to plot on the same plot the erosional velocity that we just calculated in all of these positions in the tubing, to compare them, okay, to see when I'm going to have problems. For that, I again select data. This will call V erosional. And remember, here we have to put in the x is the velocity, because the x is this axis, the horizontal. And then TBD, and it goes like that. Okay, V erosion. Let me put this a bit nicer. Okay, and the way why I do it like that, you see, it's a bit crazy way to plot data. Okay, why do I usually like to put x, everything that is a distance, I put it in the y-axis, and here we're doing the opposite. The way why we do it is because it looks more like the configuration of the well. Okay, well. Okay, if you put it like that, you can put the well just next to it. Okay, you can say, here I have my well, okay, my tubing, and here I have PWF, which will be this point, and P wellhead, which will be that point. And I can see exactly what happens with velocity along the tubing. Okay, I don't have to, if I put it like that, that's better for a flow line. Okay, when I have a flow line, I plot it the opposite, because the flow line usually is more horizontal than vertical. Okay, so that's the velocity of the gas, and here that's the erosional velocity, maximum allowed, okay, by API 14E. So what does it mean? I'm going to have erosion in this tubing, okay, due to the high velocity of the gas. That means the tubing is going to last very few time. To fix it, I have to go to the manager and say, we have to put if you want to keep producing this tubing, we have to put a bigger, this rate, you have to put a bigger tubing. Okay, because here is not so big the difference, you see? Here is like a bit close. But when you come, the pressure is reduced, the difference is very significant. Okay? So that we have checked the first step that we discussed yesterday. Okay, this erosional velocity. Did you get it? That's the next step. So if you remember last class, we said, let's say what we said. You know, we said many things. Sometimes too many things. So we were looking at this droplet balance, right? So it came from there. We're saying, well, we want to lift that droplet, therefore the sum of forces on the droplet have to be going up. And we said, well, it's going to be exactly zero when this equation is honored. Okay, and for that equation we need the density of the gas, that we already have it, right? We need the density of the liquid. The density of the liquid is going to change, it's true, with pressure and temperature, but it's a liquid, so it changes very, very, very small, okay? Not so much. So we can assume a constant number. And we have this interfacial tension, okay? That if you go on the Excel sheet, I have provided an expression for interfacial tension. And it should be in PVT is this guy, okay? Interfacial tension, and it's an expression that depends on the density of the liquid and the density of the gas, okay? Which we have both. So let's try to calculate that velocity, the critical for unloading, and see what do we obtain. Okay, so what do we have here? Interfacial tension. We have one column to calculate interfacial tension. What was the name of that function, if you remember? STOG. ST is for surface tension, which is not exactly correct. Okay, it's interfacial tension. Okay, so let's call that function ST. ST. Okay, density of the oil, of the liquid, we said won't change very much, is here, and we block it. Okay, and the density of the gas, we have done our homework, is just here, and we don't block it because we want to drag it down. Okay, and that is in Newton per meter. It doesn't change much, actually. Okay, Newton per meter. Now the last step to finish and get rid of this exercise is Turner. Okay, the velocity. So let's see the equation. It should be exactly the same equation that I showed you yesterday. It's in auxiliary Turner 546. So let's check if that's the same. I think it should be the same. Okay, 546, interfacial tension to the 0.25, density of liquid, density of gas, and this should give you in meters per second. Okay, so it's exactly that equation. So let's use it. We need the both densities and the interfacial tension. Okay, so how to call it here? V Turner, density of the liquid. I block it, okay? I have of the gas is this guy, and interfacial tension, this guy. It's B Turner, yeah, the expression. So maybe density of the gas, interfacial tension. Yeah, we are getting this number. It's very small, but seems to be correct. Yeah. So, and it really makes sense because if I'm going almost in erosion, okay, I'm going on the erosional side, then probably with such a high speed I can lift almost anything, okay, almost anything in the tubing. So that's exactly what it's saying here. Really, the velocity I need to lift it is very, very low. Okay, but we can plot it in the plot that we had before. Okay, so I include it here. So let's call this V Turner. X would be velocity TVD will be to the left. Okay, and I get this line, which tells me, remember here, being above the turner is something good, okay? Because if I'm above that velocity, it means I'm lifting everything. Nothing is accumulating in the well. So that's something good. In erosion, it's the opposite. If I'm above it, I'm in trouble. Okay, so that's what I get. Hmm? What? The Turner is this equation that I showed before. The meaning is the critical velocity to lift all these droplets of liquid from the well, okay, to avoid accumulation of liquid. So that's what this force balance is you're making, okay? You're making a force balance, and if the force goes down, the droplet will go down. If the droplet goes up, will go up. Okay, very important, this traverse plot, and now you know how to make it. You can use, there are many tools, probably if you're going to be working in the industry, there are going to be some tools that they use to do that, but now you know where it came from, okay? How do you make the calculations? Now, should we try something? Let's see now if we reduce the rate. Okay, let's say now for some reason I reduce the rate. How will that affect this line? Okay, so let's see. Sorry, here we're going to say conclusions are possible erosion in the tubing. Okay, so I need to do two things. Either to decrease QG, okay, I need to do it, or another option is to change tubing, okay, for a higher diameter. And the diameter we have here, I think, is close to 5 or 6 inch, so it's already quite big. Okay, so I'm not sure if this wall will fit a bigger tubing, but that's some solution. And then the other conclusion, that's number one. Number two is no liquid loading expected. Okay, which is that's something bad and that's something good. Liquid loading is this accumulation of the liquid on the well. Okay, that you start having accumulation because you cannot empty the liquid from the well. So which outcome concludes according to the number that will not be any liquid loading? Because for every TVD in the tubing, always V gas will be bigger than V Turner. Okay, that's the solution. And here, for every TVD, the V gas is actually greater than V erosion. Okay, in one case is something good, in one case is something bad. Okay. So I suggest we change now. Let's see if it works. I think it should work. Let's change now the rate of the well to 1 million. Okay, now we have 285. So let's try 100. Okay, you see now the pressure is not 80 anymore, but it's 53. So we have to copy that and paste it again here on the assumed number. Okay, but let's see now again our plot, how it looks like. That's the erosion. Okay, so let's copy that plot. I think that's interesting. Now, yes, now let's see this case. This case we have reduced the rate of the well. Okay, somehow we reduce it. Maybe we're going to come back later to this exercise, but okay. But here you see that's the velocity of the gas. That's B erosion, and that's B Turner. Okay, that's for 1 million standard cubic meter per day QG. Okay, so you see now in this case we can say that for all TVDs, VG is actually below the erosional, which is good, right? It means I won't have any erosion. That's something very, very good. And then also, VG is greater than V Turner. Okay, I won't have accumulation, so I'm safe. And you can play with other, because in theory, if I want to use the same tubing, I want just to be as close as possible to this line. Okay, so I can just try another number. Let's try 1.5 to see what happens. 1.5. And I have to pressure, paste it here. Okay, and see. Okay, still now I still have problems. Okay, I have here a crossing. So what happens here? That's interesting, right? So now we try with 1.5, okay? Let me just reduce that guy. Okay, that's for the rate 1.5 QG, 1.5 e to the 6. And you see, up to that point, VG is the red, okay? So from this point and below, VG is less than the erosional, which is good, okay? Is below. But above that point, then VG is greater than the erosional, which is not good, okay? So that's actually interesting. So that means I cannot produce 1.5, but I should be a bit between 1 million and 1.5. Which is significantly less than the rate I had initially. That was 283.
What the control measure to manipulate this is changing the flow rate.
Yes. You can increase wellhead pressure, for example. Let's see the effect of wellhead pressure. That's an interesting question. So let's see now. Let's go back to the same rate we had, 283 e to the 6. Okay. But now let's say, what will be the effect if wellhead pressure, somehow we increase separator pressure? Okay, we put it up to, let's say, 100. Okay. Now I have again to change this guy to the P assumed. Okay, and let's see what happens now with my plot. Okay, I'm still above erosion, okay, but I'm very close. I'm not far away like in the other case. So that means now maybe if I reduce a little bit the rate, I will be able to use the same tubing. Okay. We have to take a summary now. We have made too many changes, I think. So this well, it will be crazy. It doesn't know how to operate. Okay, so that change was if we keep the same rate, QG equal to 2.83, but P wellhead is now equal to 100 bar. Okay, that means increasing P separator or choking. Okay, you can also achieve the same by choking. Okay, and in that case now you see they're very close. So probably if I increase the pressure a bit more, or if I reduce the rate a little bit, I will be able to produce that. Okay? Yeah. But you see the power of having everything on already calculated. Okay? Now if I can change just this input in red, okay, and I can the results update automatically. Okay, so that's a big thing why we like to have all the input in red and then all the results, that I don't touch them. Basically, I change the input and see the effect on the output. Okay, very powerful. You have here your own calculator that you can use for the performance of gas wells. Okay, any question before we close? Well, not for the day, right? Just this. We're not going to leave early. Otherwise, Rui is going to chase us. Say what? Okay, that's here. Very important. I think that's all we are going to cover on tubing equation for dry gas, and it's very powerful. You can use it actually. This equation is programmed in many software, fancy softwares that you pay a lot of money to use. This is the equation used in many of these software. So,
what are the assumptions that you didn't do here, but currently are being done in your? Are there any?
The assumption? No, really no assumption. Is if you have a good data to populate your equation, it should give you very close to the measurement in the field. Okay. Some problems you might have is that the pressure has some error, the instrument is not calibrated, that the tubing really somehow it has reduced the diameter. You have sometimes in the tubing, you have another thing which is scale. Okay, like in tap water, like in the shower, sometimes you have formation of this mineral. It's like a white that is on the shower. The same thing happens on the wall of the well, starts to accumulate, and then it reduces the diameter. So it could be that you're using the original size, but it's also reduced. Yeah, the properties of the gas might be that they are not correct, but in principle, it should give you a very close result. Okay, so now let's forget about gas. Let's forget about tubing for now. Okay, I think it's because we went into the equations of the tubing, how they are derived, how they are used, and we know how we are experts now in tubing. Okay, we are really experts, but we are not really so experts is on the inflow. Okay, on the IPR. And that's what I want to discuss now. I want to talk about this gas IPR a bit more in detail. So far we said, well, we have this equation, right, that we have used, but we have to understand really where it came from. Okay, like for the tubing, even though you're going to see that only once in your life, it's important that you at least have seen it once. Okay, it's like going to, they say, what do they say here in Mozambique? That you have to go at least once in your life? That you have to go at least once in your life to that place. They say it about Mecca, I think. That you have to go at least once in your life. Okay, it's something like that for production engineer. I have to see the tubing equation at least once, how it is derived. Okay? Otherwise, I cannot go to heaven or to hell. I don't know. Okay, so that's what we are going to do here. The IPR is very important. And to start with IPR, actually, we are going to start with liquid. Okay, gas, remember, density changes with pressure. So it's a bit more complicated. So let's start with liquid. And then we are going to move to gas. because it's just to understand, it's better to start with liquid. So you know this equation that we have the rate, okay? Which rate is that? If we have a, you remember this famous experiment that I put a block of porous media and then I subject it to a difference in pressure, P2, P1, right? And then I have certain rates circulating through it. Okay. And then I obtain which equation? Those guys that are working in reservoir, they should know, John. They are crazy about this guy. Darcy, right? When you talk about with a reservoir engineer, he mentions Darcy almost like 2 times in every sentence. Okay, to start and the end of the sentence. Darcy, Darcy, Darcy. That's the Bible of reservoir engineer. Okay. So the equation delta P over delta L, okay, that's this L that I have here, times permeability, right? A property called permeability by viscosity, that's equal to the rate divided by the area. Okay, Darcy equation. Yeah. Okay, so we are going to use the same equation, but now in differential form. Okay, we want to put our snakes. We want to integrate from 2 points in the formation. So we need not just this expression, which is based on a finite system, but we have to apply it on a well. Okay, so for that, okay, let's say, and we are going to do it for a radial well. Okay, we have here our well. Okay, and we are going to assume the drainage area is just radial. Okay, maybe I have to pull it a bit down. Okay, and here I have RE is measured from here, and here I have RW, R of the wellbore, measured also from the center. And the equation in that case is Q over A over actually dA will be equal to K over viscosity dP over dR. Okay. Actually, remember, so just a few things before we go into that equation. This equation is pretty much tells you that this is like this is the local rate. Okay. And that local rate, if you divide by the area, what do you get? Velocity, right? But not really. Remember, this is a piece of porous material, right? So it's not circulating through all the area. It's circulating only through the pores of that face. Okay, if you see that up close, this area, okay, you see it's not completely open, right? So, but it has a lot of pores through which the fluid circulates. So it's not, if you want to take into account the real velocity, right? So let's say this is area. Let's call that the sum of all of these areas will be the area of the pore. Okay? So if you want to calculate the real velocity, you'll have to divide the Q by the area of the pore, right? Not by the area, the full area. But in this case, we are dividing by the full area. So that's like a velocity, and we will see later that's also one thing used for multi-phase flow. You divide by the whole area, even though the phase is not passing through the whole area. It's just passing through only through a section. Okay, just keep that in mind. Okay, so now we want to integrate this expression from, let's say, RW to a position called R, okay? or let's integrate, yeah, to a position called R star. Okay? Okay, discussion. Okay. Hot? It doesn't work? At least it's making noise, okay? So we don't know if it works or not, but it's making noise. So, okay, so to be able to integrate, right? I want to calculate from this R to R star, and I want to calculate also from PWF all the way to P star, okay? Because we were going to see something very interesting. We want to see if we use that equation, Darcy equation, that he measured in the lab, and it gave him, if you see, that's a rate, right? So you have a velocity. If you plot this, velocity and dp, dl, okay, you're going to get just a straight line, right? It's proportional. If you see that expression, this guy is this guy here, and this guy is that velocity, right? So you see the ratio between them is just K, which is a property of the formation, the permeability. It tells you the resistance the fluid has to overcome to pass through the formation, and the viscosity, which is also tells you something about resistance. But you see, it's proportional, okay? So, and that's Darcy law, okay? Darcy. It came another scientist many years after, and he said, well, actually it's not, it's like when we have on a pipe, right? If we have low velocities, then we have laminar flow, but then if we have high velocities, we're going to start having nonlinear effects, and it's going to start to deviate. And that's another guy that came later called Forchheimer. Okay, Forchheimer, I think I'm missing a C someplace. Okay, we call it non-Darcy flow, okay, or Forchheimer. Okay, did you hear that name before? No, that German name? I think it's German or Dutch. So we are going to use that expression, which will be valid only here. And luckily, that's very appropriate for flow liquids and some gases, some velocities of gas. For high velocities of gas, this is no longer valid and we have to use something else. That's why we have the n in the equation, what I told you the first day, right? This n is between 0.5 and 1. When it's 1, you have this linear regime. When you have 0.5, you are in this regime. Yeah, and everything else is in between. So let's look at, so now with Darcy, assuming I have Darcy flow, okay, I'm going to integrate that equation just to know how the pressure change when I go away from the wellbore, because we are going to see something very important that is very interesting for production engineers. Okay, so let's say, how do we express this D area? Okay, or the area that I'm going to flow. Let's not call it D area, but area. Okay. If we see what area is the flow going through, the flow is going from here all the way to the wellbore, right? That's Q. That's my rate. So if you see what area it is going through, okay, it's something like that actually, right? It's a cylinder. It's going through the cylinder. And that cylinder, if we, let's take it, cut it, and open it, like that. Okay, we come, cut it, like a piece of paper. Okay, the fluid is going through that towards the well, so that will be the area, and it will change, right, depending on which radius I am. It will be bigger and bigger, as far away I am from the well. So I cut it and open it, okay, and that's the area that I have to put there. So what is the height? I just simply call it h, right? So that will be h. And what is this length that I have here? Is the diameter times pi, right? The perimeter of the circle. So it's 2 times pi times r. And that's my area. Area is 2 pi r times h. And then I substitute that in this equation. Q over 2 pi r h equal to k over me dp dr. And now there is one small d. I have to put everything that depends on pressure to one side and everything that depends on radius on one side, okay, to be able to put the snakes. But there is one detail. If you remember, this Q is a local rate, right? It depends on pressure. So we have to put it in function to a rate that doesn't depend on pressure. And that's which one? The standard conditions rate, right? We are talking here about, this is liquid, okay, or undersaturated oil. So this is the local rate that is a function of pressure, okay? Like in gas, if I reduce the pressure, then I will have higher rate. So, but I can say that the Q of the oil, in the same way that we have done for gas, Q of the oil will be BO, that depends on pressure and temperature, right, times the Q oil at standard conditions. That's the equation that we use for the gas, right? Okay, that's Q at standard conditions. Okay, we will see later, and maybe next week when we go to multi-phase, it's very important to keep track of all of these factors, because you will have gas, you will have oil, and then you have all of these BO, BG that are important. But for now, just assume that we are using the same approach that for the gas. And this number is usually between 1.0, means an oil that doesn't matter, is not very much affected by the pressure. Remember, any liquid, if I take this bottle of water and then I put pressure on it, I have to really increase pretty much the pressure to see a change in volume. Okay? With oil, it is a bit more sensitive to pressure, but not much. It can change from 1.0 maybe to 2.0 if it's a very volatile oil. Okay? And this is a very dead oil, just almost like a water-like oil. Okay. Now I have that, so I can express that rate, local rate. Let's express it. So we say Q, that will be BO times QO divided by 2 pi RH equal to K over MO dP dr. And we are ready to integrate. We have to separate variables. So we move everything that has to do with pressure on one side, everything that has to do with radius on the other side, and we are going to have a constant someplace. So what depends on pressure here? The properties, right? BO and the viscosity has some dependence with pressure. BO, MO, BO, integral of that, and there I get dr. We have here QO. This is a constant. This is a constant. to this pi is a constant, and then we have the integral of h is also a constant, and here we have just r. Yes? I think so. QO 2 pi HK, I think is correct. Okay? And now we integrate, like I said, from the wellbore to a radius called star, which is going to be, you're going to make the plot now, and PWF from the boundary where I know the pressure, I measure it somehow to the reservoir, to P. And the assumption is, if you see that in every position, I have the same rate. Okay, I have the same standard condition rate. So I integrate and I end up with, we may put it to the right. So those of you who are taking classes with Kalashnikov, what does it give? This expression, ln of R over RW. Then I have QO over 2 pi KH. This integral, if you have a fluid that, let's say, is ideal, okay? No, it's not real oil. It's more like close to dead oil. If you have dead oil or ideal, okay, let's say that MO and BO are not affected, are not a function of pressure, pretty much. So you can take them out of the integral and just have dP, and here you will have PW F minus P minus PWF. Okay. Very important. We are now very close. You see, IPR, I told you we have a difference in pressure, okay, and we have the rate, and we have a constant. We are very close to getting our IPR equation that we need. So to use this equation, and you're going to use it now in this next exercise, I'm going to say I'm going to clear pressure as a function of radius. I want to plot the pressure as I move outside of the wellbore, how the pressure will change. Okay, so let's do that. Let's say, so you have QO times MO BO divided by 2 pi KH and ln of R over RW equal PWF plus, and this will be P, right? I hope. I think so. Yes. Okay. So before we go to IPR, we are very close now. We are just some steps ahead we need. But before, let's plot that. For that, we have an exercise. I'm not sure if it's, I think it's a class exercise. Yeah, this is a class exercise. The next one will be a graded exercise, where I have that data, okay? And I'm going to plot the pressure. So let's say here a radius, okay? Radius, let's create here. It's called pressure distribution radial well under saturated oil. That's supposed to be that. And that you find on my website on the under class exercises. So please download it and we work with it. Okay, so we're going to create two columns. One with R, okay, that will be in meters, and one with pressure, and the pressure we're going to have it in bar. Pressure distribution radial well under oil. And we are going to start, the first point of my plot will be well bore, where I know you have this bottom hole pressure that I somehow measured. Okay? By the way, there is something I forgot to mention here, that this equation is in just pure SI units. Okay? Okay? So this is in pure SI units. Okay? If you're going to use it in field units or in bars, so you have to change. So if you use viscosity in centipoise, if you use pressure in bar, if you use what else do we have there? Q in standard cubic meters per day. Yeah, the permeability will be millidarcies, and age will be in meters, I think. Radius will also be, here doesn't matter because you have the ratio between them. Okay, so it just matters that they are in the same units. But let's say radius in meter, then the equation, you have to add a factor, okay, which is just to convert with the units, and the factor is 18.42. Okay, 18.42. So going back to our Excel sheet, okay, let's say maybe you can press Alt F11. Okay, Darcy law, assuming Darcy, okay, that was the first assumption. We are in this linear regime, nothing else. We say that the pressure will be equal to PWF plus exactly the same expression I wrote in class. Okay, Q, this U is the viscosity, VO, K, H, and the log of R over RW. Okay, so let's say what is the extension of my reservoir. We don't have it, right? So let's make it maybe, let's say 500 meters. Okay, so the first point will be well bore radius, 0.1. Which radius I'm using here, by the way? Which radius is that? Is that the tubing diameter? Is the one that is in contact, if you remember the okay, if you remember how the well is constructed, you have the hole, right? And then you run a casing, maybe cemented in between. Okay, and then you perforate. Okay, make some perforations. That's for some type of wells, okay? Okay, so really the radius that is in contact with the formation is the radius, this RW, okay? The one that is in contact with the formation, that is the radius of basically the production casing. Okay, so in our exercise, we are going from point 1, and then we have to go all the way, let's say 500. Okay, let's say that the outer boundary of the well is 500. How do we do that expansion from point 1 to 500? What numbers do we put? Where do we want to plot pressure? Remember that to plot it in Excel, you have to put points, right? Where you want to calculate the pressure. So which radius should we use? Let's try first. Let's say 1 meter. Then will be the next one will be 2 meters. 500 will be too much. So let's see 5. Then maybe 10. Let's say 15. 25. Let's say 40. And from here, from 40, let's go if we put, we want to go to 500, right? So let's use this one plus 40. Okay? 400, 500. You can use any numbers you want, but that's my suggestion. Point 1, that's the first point. 1, 2, 5, 10, 15, 25, 40, and then in steps of 40. You got it? Yep. Not yet. No, I'm just putting random numbers. You can put your own numbers if you want. Okay? That's numbers decided by Milan. Okay, I took the top of my head. 1, 2, 3, 5. It's not that God told me anything. No, I just chose. But if you want to have the same results, you should use these numbers. Okay, just such that you can QC. What is the pressure at wellbore radius? The pressure at wellbore radius? No. PWF, right? Exactly here, I'm going to have PWF. When I start to moving out in the reservoir, I'm going to get close to PR. Yes? Okay? Because otherwise I won't have flow. Okay? If the pressure here has to be higher than here to move on that direction. Okay? So here will be PWF. Luckily, let's see if I have it here, 110. Somehow they measured. And for the other pressures, for the other radius, I have to use the equation. Okay? The equation, let's see the name. I think it had Darcy. Pressure distribution in metric. Pressure, viscosity, KH, Q at standard conditions, BO, R. That's the position where you are, and R of the wellbore. So let's use that equation. We go Darcy, Darcy law, pressure distribution in metric. And here we use that pressure, which is PWF. I have to block it. That will be the same for all points. This U is not velocity. Don't be confused. That's viscosity, which I have it here, 162. Remember, water is 1 centipoise. Okay, so 162 is like 50% more viscous than than water. It's like a bit less viscous than car oil. Okay, more or less. Then that I block it also. The viscosity will be the same. Remember we said it doesn't change. That's why we could put it out of the integral. KH, I don't get the both separately, but I get the product. And that's because sometimes of well testing. Okay, in well testing, when I measure that, I do some tests to measure KH, and I cannot really say what is from H and what is from K. So I put both of them in the same number. KH, I also block it. Q, the rate that I'm flowing from the well is this 210. Okay, it's a very low rate. It's like 1,000 barrels. And that I have to block also. I have a bunch of input. BO, the factor I told you, that is a ratio between local rate and standard rate, oil rate, is here, B, 1.24. I also have to block it. Remember, we have to block it, otherwise we are going to get a party here of errors. R, that's the position where I want to calculate my pressure, okay? So that will be the guy to the left. And R of the wellbore is this guy here, okay? The first one, and I have to block it. $125, that's what I'm getting. The pressure is increasing, which makes sense. Okay, well, when I'm going away from the wellbore, the pressure should be increasing. Okay, and then I'm going to drag it down. Okay, are you getting similar numbers? Okay, so let's make that plot. Did you get a similar plot? Okay, before we take a break, we have to discuss a bit this result. Okay, we got. So that's this exercise. and that's not a mandatory, that's a class exercise. Okay, so what do you see, what happens when we are very close to the well? How is the pressure changing when you are very close to the well? Okay, within the next, let's say, 20 meters. It's changing very dramatically, right? It's changing, you have a very sharp increase of pressure. But then after that, as you go away and away, it's just stabilizing, okay? It's just getting very, very flat. This plot is extremely important for reservoir engineers. You remember how the equation looked like for production, the Darcy equation for radial flow. How did it look like? Is Q divided by area equal to K over dP over dr, right? That was the equation. Now, what is the derivative with respect to radius? The derivative of this curve, how does it look like? You remember what, yeah, Kachalnikov, is it? What he taught you, right? If you have a function x, is that the if you go on a point, you want to calculate the derivative, that will be the tangent, right, of that point. Or if you have it here, that will be the derivative. Here it will be close to 0. And if you have it here, you have a negative derivative. So here the derivative of the function is negative. Here the derivative of the function is 0. And here the derivative of the function is positive. Okay? So, and you see here the derivative of that pressure is really what is giving me the rate. Okay? So if you see here, the derivative is almost, on this area, is almost very close to 0. Okay? So here you have almost no contribution to the production. Okay? But when you go very close to the well, that derivative starts to increase very, very much. Okay? The angle, it becomes to very, very high. So the contribution to production or the highest pressure drop, let's call it like that, sorry, the biggest portion of the pressure drop occurs very close to RW, okay? Extremely close to RW. We are saying here within maybe the first 100 meters, okay, or 50 meters. Extremely close to the wellbore. Even though we have 500, it's only in this range where you really have, yeah, it's like 20 or 30 meters, okay, not 50, actually, first 30 meters, okay? And that's really what determines the productivity of the well, okay, because of that equation. And that determines okay, so for a production engineer or a reservoir engineer, it's very important to see how that pressure outside of the wellbore is changing with time, okay, this pressure. And it's going to change very slow and very uniform. But for a production engineer, we really don't care too much about what happens 30 meters, 40 meters away from the wellbore. We just care about the near wellbore region, because that's where most of the changes in pressure happen. They are more sharp. This derivative is highest, and that's what affects most productivity. Okay? That clear? Yeah? Okay. Let's take a break, let's say 20 minutes. Okay, and then we come back for now we are going, after we have that expression, the next step is we are going to see how do I calculate IPR from this expression. Okay, we almost have it. Okay, we have a pressure and we have a rate, but we have to include there somehow reservoir pressure to get the expression of IPR. Okay, so it's a bit different when we talk about gas or liquid.
Why is it important to identify this point where the pressure drop
It will be different for every reservoir, okay? But what I'm saying is that for production engineer, you have to be careful of what happens close to the well. You don't care something that happens 1 kilometer, okay, 2 kilometers away from the well. Really, what affects the production of the well is what happens in the close region to the well, okay? And I'm saying here for our case, 30 meters, okay? But for other case, might be different. Might be 5, might be 100, okay? It depends, but it's always close to the well.
so that means
Okay, let's go back. Okay, so that was a small detour. Okay, we just want to see that it's important to show you that we want to really, what's happening very close to the well is very important for a production engineer. Okay, but really our intention is to find an expression when we calculate IPR, okay, inflow performance relationship, that will give me the rate with if I introduce reservoir pressure and flowing bottom hole pressure. Okay, so for that, let's say something first about that reservoir pressure. Okay, that will be a bit. So the reservoir pressure is actually the average pressure in the reservoir, okay, in the drainage volume that I have. So if you have, like in the previous case, right, you have P and you have the reservoir, the R, okay, and then you have a very big change like that. That will be up to RE, okay, that's the extension. If you remember, I think it was not yesterday, but the day on Wednesday, on Tuesday. So that will be the boundary of the reservoir, and that will be RW. Okay, so it's the average pressure in that volume. To calculate that pressure, you have truly to make an integral on pressure dV divided by the volume. Okay, from RW to RE, and from RW to RE. You have to, that's how you calculate the average pressure. Okay? So you can find, we are going to take here a shortcut, okay? You can go to the full equation and try to integrate and try to find that, because we want to find first an expression of that reservoir pressure. Um, we want to find an expression of that reservoir pressure to substitute it in our equation, okay, that we already have. So the location, the way we are going to make it is reservoir pressure, the location, reservoir pressure is like, it doesn't exist, it's just an average, right? An average pressure of the drainage area. But because the pressure changes from this PE all the way to this PWF, okay, you will find a place in the reservoir where the pressure is exactly equal to reservoir pressure, okay, just by chance. Okay, let me make that a bit more pronounced, this curve. Well, okay, you have here PWF and here you have REPE, okay? Reservoir pressure is the average, okay? So at some point, you're going to have that pressure, that reservoir pressure at some radius star, okay? Now, and if I find that radius star, it's a big success, okay? I can just use, on my equation, I can know the value of, if you remember the equation that we were using, it's QO, let's maybe bring it from here, okay, this equation. Okay, this is one way, and it's to avoid more mathematics, okay? Because if you try to derive it from fundamentals, it's a bit more complicated. But we have that expression, right? So we say we want now for this pressure, that's something that we can measure. If we shut in the well, all the pressure will equalize, and I reach this average pressure. Okay, all the pressure will equalize. So I want this to be PER. So to substitute that equation and that I have only the rate, where is the rate here? Is not the rate is not here. Should be here, I think. That's a mistake, okay? Good thing that we copy the equation. QO. Yeah, here we have QO. Not sure why I forgot it. Okay. So if we want to substitute P here, we have to substitute also a radius. It cannot be, and the radius, so the radius is like a radius at which reservoir pressure occurs. Okay? Even though reservoir pressure is this fictitious pressure that I get when I close the well. Okay? But it will happen at some position at some radial position. Okay? And if you remember, there are two types of boundaries, right? We have, well, we can make it here. Okay, we have two types of boundaries that we discussed, on Tuesday. What were those? The two types of boundaries we have. One type of boundary is constant pressure, all right? That we call steady state. Okay, if PE is constant, that we call steady state, right? And then we have if Q is 0 at RE, that means that it's isolated. Like if I have a fault, okay, there is no fluid flowing through that boundary. If I have the pressure is constant, it's like if I have water injection, okay, fluid is being pushed towards that boundary to keep the pressure constant. If not, then the rate is 0, okay, and how do I call that regime? Okay, I have no flow here, then that is called PSS, okay, pseudo steady state. We mentioned that already. So after doing some math derivations that I'm not going to show here, so for if pseudo steady state, that means PE is constant, reservoir pressure occurs exactly at R equal 0.61 RE. Okay, let me check the number. Point 61 RE. Okay, so a bit more than half. If here I have 0.5, it will be a bit more than half. That's where I will find my reservoir pressure. That means if I go somehow, okay, on my well, if I go with a pressure meter and I punch it in the ground all the way to the reservoir, exactly at 0.61 RE, I will find reservoir pressure. Okay? That's not something we normally do, right? It's very difficult to punch it and just measure. Just like the doctor, they put a needle on you and they measure something, okay? We cannot do that to reservoir. But if we could, that would be a fantastic way. I don't have to shut in the well. I just go, I walk until I reach exactly 0.61, measure, this is reservoir pressure, okay? I don't have to do any shutting, okay? Unfortunately, we don't do it. Now, the other case, if I'm in pseudo-steady state, that means that no flow, okay, at RE, that means that that reservoir is isolated, is going to decline with time. In that case, PR occurs at 0.47 RE, okay, which is a bit less than half. Again, the same thing, if I punch there and then I measure, that's the pressure that the reservoir has. So let's make that and let's substitute for both. So for pseudo-steady state, I get PR minus PWF, okay? Then I multiply times 2 pi K H divided by ln of, and here I have to substitute R is where I have reservoir pressure. Okay, that will be 0.61 RE divided by RW. Let's see what else. MO BO is equal to Q. Okay, and 0.18, 0.42. I'm always forgetting something. Okay, and that's exactly very similar. If you remember how did the IPR equation look like for liquid? What we discussed on Tuesday. If you remember for liquid, the IPR was PWF versus QO was a straight line, right? So if you look at that equation, this is a constant, this is a constant, constant, constant. These two are properties. They depend a bit on pressure, but for now we are assuming it's ideal liquid. Okay, so they are constant. This is a constant, and this is also a constant. So that's a constant. If I make now, I call all of that, I call it J, okay, which is the productivity index. Okay, I'm going to end up with this expression, PR minus PWF times J equal to QO, which is essentially a straight line. Okay, when PWF is PR, I get 0. When PWF is close, I get maximum rate. Okay, and I got my linear, yeah, and it comes from the equation, okay, from just the laws of physics on the reservoir. Now, there is something that we have to mention here. Let's go back to this 0.61. So we can, so let's rearrange that, okay? QO equal to, you will see now why I'm doing this. It's just another way to express, it's the same equation, but I'm going to express it in a slightly different way. Okay, and I'm going to say ln of RE over RW, okay, and plus ln of 0.61, right? Is that correct or not? Yeah. I just separated this 0.61. Remember the ln of A times B equal to ln of A plus ln of B. Yes? Okay, so I have done that. You will see now right away why. It's just a small change on the equation. Can someone calculate what is ln of 0.61? Your computer? Or 0.49. Okay, so essentially 0.5. Okay, minus 0.5. So that effect, this represents, okay, this 0.35 is the effect of the boundary, okay, the type of boundary type, which is constant pressure. Okay, is 0.5, and to see the effect it has, Let's see now what is that number. How much is that number? Do you remember what in our example, what numbers did we use? Is ln of RE was 500, right, meters, divided by 0.1 meter. So how much is that? 8.5. So see really, and what's that effect? What is the relationship between the ratios? That's a convergence, right? Because I reduce the ratios, the ratios, and I'm getting a less area to flow. Okay, the area becomes smaller and smaller and smaller. So that's where this line came from. So this effect is effect of the convergence. Okay, when the area becomes smaller and smaller, when I get closer to the well. And if you see that the boundary really doesn't make much, okay, it doesn't change much, this 8.5. It's much bigger than 0.5. So really, this number is not very important. Now let's do the same for pseudo-steady state. Okay, exactly the same. So what are we going to get in that case? QO, exactly the same equation. So for PSS, okay, 2 pi KH over BO. And now is 0.47, right? And how much is 0.47? Again, 9? Minus 0.8. Are you sure? No, 775 something? Huh? 75, okay. Okay, 0.75, and this guy still is 0.5, okay, for our case. So that means you see the difference of the boundary between steady state and pseudo-steady state is 0.25. It's very small, okay? And that makes sense with the result we calculated before. The boundary, what happens outside, doesn't affect much the well. It affects very little. What affects is really the convergence, the effect that you have on the very close to the well. That clear? So if you have J, this guy, so all of these will be J, okay, for pseudo-steady state, and all of these will be J for steady state. Here. So let's make an exercise. Let's calculate for the same well that we have here, that we have done before. Let's calculate this J, okay, and the IPR. So for that, we have to create another column called PWF, right? And that will be in bar. And here we have the Q of the oil. And that will be in standard cubic meter per day. And I think the equation of J, I have already, let's see if we have it, Alt F11. Productivity index, okay, J, is the second equation is listed here. Okay, so we are going to use this equation. Just before, here we need K and H separately. Okay, so let's modify this equation such that we can use it. So, very carefully, put the cursor in front of the H and erase all the way to the comma and put the KH like one variable. Erase the space and the comma between K and H and put them together, K and H, such that is one variable. And now on the equation, do the same thing. Erase space, star, and space. until KH is just one variable. Okay, because we don't have KH separately. We have the two things together. So let's use that equation. Okay, be careful. They have to be together, otherwise it's going to complain. Okay, Excel will complain. Okay, now we go back to the Excel sheet. Let's create here a cell called J. What are the units of J? Okay, we can get it. We know that we could get it by looking at all the expression, right? But it's much easier to say that J is a rate divided by a pressure, and the rate is standard cubic meter per day, and this pressure is in bar. Okay, so that's the units of J. So let's write those units to the left, to the right. Standard cubic meter per day per bar. Okay. Now in this cell I8, okay, let's apply the equation. The equation, the name of the equation is called productivity index, JM. So let's find it. Here, okay, productivity index. So we need KH is here, viscosity is here, BO is here, external radius, we don't have it here, what we said is 500, so I just say type 500, and the wellbore radius, we have it here. And we need one more thing, which is S. This S we are going to cover just in a moment, okay? That's called skin. Did you talk about skin before? Skin before? No? Okay, that gave me 4.12. What is the meaning of that number? It has a physical meaning, okay? That means for every bar, right, that I reduce the bottom hole pressure, I'm going to get 4 barrels. For every bar, I get 4 barrels. For standard cubic meter per day. Did you get a similar number?
Yeah.
Yeah?
The 500 is the reservoir.
Yeah. The outer radius, okay? The boundary. And that I know if what is the extension of my reservoir, if there is a fault there, or for example, what is the distance between 2 wells. Okay, that will be someplace in the center. Now to plot IPR, I need PWF. And remember, PWF goes from reservoir pressure all the way, we can put it down to 0. Okay, so reservoir pressure is 164. That will be my first point. And then I suggest we use 150, 125 maybe, and we go and drag that down. Okay, all the way to 0. The formula of J? We are going to discuss later. Okay, then the rate of oil will be simply the J, which I have to block, okay, times open parenthesis PR, and I have to block that number. If all the points will have the same PR, right? Minus PWF, and in this case is the same. Okay, actually I should take maybe reservoir pressure from here, okay, and block it, minus PWF, and I get those numbers. And I'm going to plot it, okay? Just wait a moment. X will be the rate. Okay. The pressure. Okay, exactly what we expected, a straight line. That's not radius, that's rate. Okay, let's go back. So you now found we plotted this guy, and just also to make a point, or make emphasize something. If you come and you measure, right, you ask to your petrophysicist, you ask to someone in the company to give you all of this information. You can compute J, and you can say, theoretically, your well is going to produce that much. And you go and test it, and actually it doesn't produce that much. How do I test the well? Just to see, how do I test? We talk about testing. How do I test the well? Okay, I have to find out the IPR, okay? To find out, I want to know the IPR of my well. Okay, remember I have a component called choke, okay? So first I say, and this is producing, let's make something here. This is producing to a separator, and in my separator I have a valve for both phases and then I have a meter, okay? And in this meter is that I record the rate of oil, okay, at standard condition. So the way I do it, I go to the field, okay, that will be time, and that will be rate, okay, the well is producing a certain rate, okay, and you record, so you remember, let's say you have a gauge, okay, you have here a meter, okay, that is measuring the pressure, and you have a line going up, and you measure this PWF, okay, you're measuring this pressure. So if we make another plot here, the same plot with the same time, but now it will be PWF, okay, and I'm measuring a PWF, okay. Of course, the value is not constant, but it's, fluctuating a little bit. In life, nothing is constant, okay? Everything is going even fluctuating very much. Okay, now I go to the field, make a test. That's one point, okay? Now they say, well, make another rate. So they lower the rate, okay? And they measure the rate. And then they do by choking the well. And that will give you, okay, another PWF. So that will be, let's put it here, Q1, PWF1, PWF2, QO2, and then I even choke it even more, okay, QO3 and PWF3, okay. So I take these three measurements, and if I say 3 points, it will take more time, okay? Because initially it's very difficult to stabilize, and this pressure, might actually do something like that, oscillation until it's constant, and then you have here also oscillation until it gets constant. What happens now if you plot these points? You plot the combination of QO and PWF, PU, how will it look like? Q oil versus PWF, okay, the ones that you measure. If I plot the first point, where is it gonna be? It's a high rate and low PWF, okay, QO1 and PWF1, okay. The next point, let's say, is here. QO2, let's put it a bit lower. QO2 and PWF2, okay. If it's an undersaturated, this is an undersaturated reservoir, oil reservoir. Okay, where should the third point fall? The third combination of P, QO and PWF3. Huh? They should give you a line, right? Exactly the solution that we found now. It should be a line. So the third point should be, if I follow a line exactly through these 2 points, okay, the third point should exactly fall here, okay, QO3 and then PWF3. Okay, and this is actually this expression initially, the expression of an undersaturated, this expression here, it didn't came from analytical derivation. No one that was a very fantastic mathematician. It came from measuring in the field. People came and they did exactly that test. Okay, and they plot the points, and it gave them a straight line. That was a guy called Millikan, around the 1930 something, okay, 36 or 33, I think. He made exactly that test, plot all of those points, and showed it's a straight line. And some years later came people saying, well, if you do the math, if you derive the equation, you obtain the same expression, okay, which was very nice. Now, I ask you, if it's an undersaturated oil well, is it necessary to do so many points? Remember, each point costs money. If you give me 5 points, 10 points, each one of them will take a few hours from a day, okay, from 2 days, okay? So you don't need really, remember a straight line, you can use it only with 1 point or 2 points, okay? If you have reservoir pressure, if you have this point here, reservoir pressure, you already have reservoir pressure, you already have 1 point, right? 0, comma, reservoir pressure. And if you have another point, which will be, let's say, this one, QO2, PWF2, you have 2 points. You have everything you need to have the line. So that's one comment. Okay, that was measured long time ago in the field, and it matched the equation, which is nice. And also another comment is that that equation will probably won't work out of the box. Okay, if you say I have all the parameters here, I have measured, they are perfect, I put it, and then I test my well, okay, probably there is going to be some difference. Okay, so if we make a, let's say here a comment, so IPR equations don't usually work or don't have high accuracy when let's call it analytical, don't usually have a high accuracy. Okay, that means that if you make your measurements, so if you plot your equation, right? You say you take, I have PR and I plot my equation. The well is supposed to be a very nice producer. It's supposed to give you a lot of rate. And then you go and plot the points that you measured. Maybe they are like that, okay? A big disappointment. You go to your boss, you say, I have a plan. You say, if you produce that reservoir and you drill that reservoir, you're going to get this red curve. And then you get a big bonus, then you can buy a car, you can do many things, okay? Then they go and drill the well, and actually, okay, something happened, okay? There are many reasons for that. Huh? So either you have to run, okay, they're going to fire, or yeah, something. But there are many uncertainties in this equation, okay? One of them is the fluid properties. You take a sample of the fluid here, but in reality it's under some other conditions, okay? We try to measure under those conditions in the lab, pressure and temperature, but you might have some uncertainty there in the fluid. But the biggest uncertainty really is on the reservoir, okay? What is RE, the extension of the reservoir? What is the permeability? Maybe you measured in one place, but you're not sure if it's the same, if it's uniform along the reservoir. And also the age, okay, the height of the reservoir. Maybe the geometry is not exactly radial, okay? Don't have high accuracy. She doesn't like IPR, so okay, don't have accuracy, so let's call it right out of the box, okay? Out of the box. You cannot just go send values inside and say, I trust my IPR 100%. You cannot, okay? You always, so I just want to put the message here, always do testing, okay? Testing in the field. Always. And then you can adjust your IPR, your equation, such that you reproduce the number. You have to be, it's very important to have the shape, because if you say, well, with time now, if I have the slope, I know it will change something like that, okay? So I have what will happen with the future with the web, okay? So that is, but always do testing to verify your IPR. Let's, in the time we have, let's talk about this S factor, okay, that I took here. S is called skin, okay, and skin refers to really to all. So let's call it flow impairment. Flow impairment. So sorry, let's do something else. S, yeah, is flow can be a few things, okay? Flow impairment near the wellbore, okay? And we will see a bit what do I mean by impairment. When we drill the well, okay, when we are drilling, okay, we know we have a bit, right? And the bit is causing some, is rotating and is scratching, is crushing the soil, and a big part of the drilling process, you're pumping mud, right? Through the tubing, through the string. You're pumping here some rate of mud. What is the purpose of this mud? What is the purpose of this mud? Has many, okay? One of them to take out the cuttings. Whatever you're crushing, it takes it up to the surface. To, yeah, to cool, for cooling, such as you won't have. What else? Yes, to avoid that you have inflow from the formation. The cake. The cake is what we don't want, okay? So that's the whole point. When we drill, we get part of this mud that we have here, okay, that is filling the whole cavity. Part of that mud is starting to accumulate and build up here, okay? So that's what production engineers we hate, okay? These guys, it's something that you have because of the drilling process, okay? But if the mud starts to permeate and goes not much, okay, a few centimeters, okay, maximum maybe a meter, but goes a bit far in the formation and stays there. And that mud, the thing is that it changed. That mud has a lot of minerals, a lot of things that are also solids, and they stay in that part very close to the wellbore. And if you remember, what did we discuss just before? For a production engineer, what is really very important is just the region close to the well. And then comes this driller and just, yeah, takes a dump or something close to that region, okay? So that's why production engineers, we don't like too much drillers, okay? So for that case, this is, for example, something that is production impairment, okay? That is something that after the fluid comes here, well, now it has to go through a damage, okay? It's like, so that's what we call formation damage. Yeah. We also can have, due to the perforations, okay, because it is related to that, to the previous case. Where is it? Okay, here. Okay, here in reality we're not flowing through the whole well, but we are flowing first to these fracs, and then we are flowing through the fracs inside. Okay, so we have some sort of a convergence effect. So that skin we can also have it there. Okay, but we can also have flow enhancement. So let's leave it flow impairment, okay, just for now. So how do I account for that skin in this equation? Okay, so how do I include skin somehow in this equation? We will see, so the effect it has is if we plot our wellbore, okay, let's plot here our wellbore, and we plot, okay, our pressure versus radius, right? In reality, let's say we have, ideally, okay, we are going to have this distribution, okay, going from PWF 2PE. Okay? But in reality, and that's the one that is given by the other equation, okay? Ideally, I have no skiing, nothing. But in reality, I have a lower pressure. Okay? In reality, to flow, when you flow that rate, in reality you need a lower pressure, okay, which is the real PWF. That's the one that you predicted from your equation. You say, well, to produce that rate without any skin, okay, you use that equation to produce that rate without any skin, any damage, okay. I will need this pressure, but then you start flowing and you actually have this pressure, okay. So you have these two distributions. The first distribution, like we already discussed, PR minus PWF. So that is the ideal, okay, without skin, without damage. Okay, and this is the real, okay, with damage. Okay, so we make a trick. The trick is the following. We say the ideal we can express as PR, okay, PR, and remember both of them are for the same rate QO. One of them was the one predicted from the equation, the other one was the one that I actually measured. Well, I really need to lower much more the pressure to get the same rate. PR minus PWF star is equal to is 18.42. What was the expression again? B mu divided by KH times ln. Is that correct? RE over RW, and I have to have QO someplace here, minus 0.75, for example. Okay, yeah, I think it's correct. Okay, so that's one. That's expressing the delta P of the of the real. Now the delta P of the real PWF, what actually I am producing, I'm going to express it in the same way. Okay, it's just a trick. I'm just going to express it saying 1842 BO MO QO over KH. Okay, so now I'm going to use an S here. Okay, because all of that is a constant. Okay, that depends on the actual wellbore. And now I'm going to put the real pressure drop with an S. Then I'm going to add up both equations, and I'm going to end up with this equation, PR minus PWF. It's just a trick, okay? I know that there is a pressure loss due to skin. Sorry, here it shouldn't be PR, it should be the skin, okay? The pressure drop due to skin. Okay, is the real minus the ideal. Okay, that is actually what the difference between these two guys. Okay, what I measured, what I really need to produce QO, and what I predicted. Okay, this is the delta P of the skin. Okay, so I make this trick. This is the ideal. Okay, and this is the skin. Okay. And then what I say, well, that delta P, I'm going to express it as this number times an adimensional factor called S. We will see now why this is a bit confusing, but why are we doing that? Okay. But basically, the idea is to make adimensional the pressure drop. Okay, I make it adimensional by taking this guy here, which is a constant, and then I just put it in front of this S. Okay, when I sum up both equations, I end up with the following: 18.40. Okay, I end up with that equation, which is almost exactly, if I rearrange now, I get QO equal to, sorry, which is, this one will be now the real. Okay, now I took away the ideal, I don't have it anymore, close the skin. Okay, and now by using that term, if I measure the real rate, the real PWF, and all the rest, I use data from the field. With this S, I can say, well, now there is some impairment. Okay, there is some damage on the formation that I can use to adjust to know exactly to get the rate that I'm measuring in the field. Okay, and this S typically, that's why we said in our example is 0. Okay, what you were asking before, why do we put 0? 0 is no damage. Okay, that means original reservoir. Okay, S positive, that means damage. Okay, and it's usually a number can go all the way between 0 and maybe 10. Okay, you have very severe damage, or it can also be used for it to be negative. Okay, if it becomes negative, remember this is 8.5, right? Or around that number. This is 0.75. And this number, if I make it somehow less, what happens if now the denominator becomes smaller? The rate will be higher, right? So this is also to model stimulation. Okay, stimulation, I come to my damaged well after I have finished my drilling process. I go and inject some acid such that it can dissolve some of the particles that are close to the wellbore, and then you try to reinstate the original productivity of the formation. Okay, so that's why sometimes I use this S. And S is called, I'm not sure if they put it here, but it's called the skin factor. Okay, skin factor. So to finish for today, I think we have had, I didn't get to gas, okay, so that we're going to cover tomorrow. It's similar development. The main difference with gas is that this BG is changing, okay, with pressure. So we have to have an integral that we have to know what to do with it. But it's exactly the same procedure, okay, exactly the same that we have done here. So just to finish, we are going to make this exercise where we're going to make another curve now with skin, okay, minus skin 18, okay. This was skin for 0, and let's do now a plot for skin 18 for a damaged well to see what will be the difference in the curve. So let's put here, this is for S equals 0, and let's make one here now for S equal 18. And we are going to use the same PWF, but now we are going to use this skin. Okay, we have to calculate another J. So this is J for S equals 0. S equals 0. And this will be J for S equal 18. And we can copy almost the same equation. I can copy the equation like that. Okay. But now I come and change it. I have to take now this S won't be 0, but will be 18. So you see the productivity index was reduced dramatically, 1.25. And now I use, this will be J, I block it, times PR, which is here. I block it also, minus PWF, which is here. And I get these numbers. Then I plot it. I'm running just because I want you to do it yourselves. to have a party in the